my name is Matthew. Today's question is, what makes a cell cancerous? Well, it usually starts with a mutation in the DNA. Our DNA is the basic structure on what makes us, well, us, like why we might have brown hair or green eyes. Once our DNA is mutated, well, it takes more than just one mutation, like any other disease or sickness, for it to actually become a problem. Like, your doctor's not gonna go, "Oh my god, this guy has cancer because he has one mutated DNA cell." No, probably he'd get fired because he can't overreact like that. Unfortunately, a lot of us already might have cancer cells in our body, but that doesn't mean it's gonna kill us in like 20 years. Right now in 2018, there's about 5,060,000 people dying of cancer every year, which technically we're not at the end of the year yet, so hopefully that drops by the end of the year. But we're pretty close, so I don't think it will. Anyway, let's get back to our main topic. What does make a cell cancerous? The answer to this question is honestly pretty complicated, so please stick with me here. Cancer is developed by a unregulated, God, I cannot speak, cell division, or to divide without respect to normal limits. They spread and destroy tissue, which is this pink stuff right here, then turn normal cells into cancer cells. Our body, on its own, tries to defend against the cancer cells, but usually, if the body's not strong enough, the cancer cells usually win, and that leads into a lot of bad things, which then normally results into, death. But sometimes our body can win, so let's not get too sad here. Then, if our body wins, we usually don't see the cancer cells for a bit. Why do I say a bit? Because unfortunately, they usually come back. This process of turning normal cells into cancer cells is called carcinogenesis, which isn't good, as it's kind of obvious, honestly. It's not good, and once it happens, a lot of hell can go down. Mutations in the DNA of cancer cells typically affects two general classes of genes, oncogenes and tumor suppression genes. In normal non-suppressor genes, the products of proto-oncosis promote cell growth and mitosis prior to cell division. Thus, proteogenic cells encode proteins needed for normal cellular functions. I'm gonna bring this up real quick. We have no known cure for cancer. We've been trying to find it for like 40 years. But since we haven't found one yet, that's why so many people die from it. If we had a cure, which we do have treatment, but that rarely helps with anything. But if we had a cure, a lot less people would be dying. And honestly, that'd be great for the world, because we need people, or else we're all going to die. Mutations in the proto-oncogenes can modify their expressions and functions of the gene product, which is pretty bad because if our cells didn't function, we would all be dead, like right now. Cancer also makes you pretty sick, which is why I'm all red right now. But most diseases do that anyway, but they don't kill you. But cancer is different because that's what it does. It kills you. Phew. Alright, I'm feeling better now. But now back to our topic. Once the proto-oncogene is mutated, it increases the amount of activity of the product protein. When this happens, they become oncogenes. Then the cells have a higher chance of dividing more and more and uncontrollably. They then get abnormal properties. The product of those abnormal properties is protection against cell death, loss of respect for normal tissue levels, and become part of tissue environments. Wow, these cells sound like a bunch of 5-year-olds. Meaning they have no respect for anything. I want to go on an entire rant on why I hate 5-year-olds, but I can't do that, so I'm just going to get back on topic. I do hate them, though. Anyway, so the reason that... you're wrong. Wait, what? I'm wrong? Yeah, you're really wrong. Well, what do you mean? You're doing a project on it. Wouldn't you know everything about it? Well, no, I'm just a 6th grader. I don't know everything about cells. Well, that just means you're stupid. Okay, back to topic. Hey, shut up. trying to make a project over here. Proto-octanogenes cannot be removed because they are vital for growth, repair, and homeostasis. It is only when they become mutated that the signals for growth become excessive. In normal cells, the products of tumor suppressor genes temporarily discourage cell growth and division to allow cells to finish routine functions, especially DNA repair. Because if it wasn't repaired, it wouldn't be good. We'd all mutate and then probably die. I don't know how it works because I'm not a scientist, but that's just my idea. That's just theory. My own dumb theory. Tumor suppressors are generally transcription factors activated by cellular stress or DNA damage. The function of such genes is to stop the cell cycle in order to carry out DNA repair, preventing mutations from being passed on to daughter cells. Hey, where are my son cells? However, if the tumor suppressor genes are unactivated, then the DNA repair cannot occur. Tumor suppressor genes can be inactivated by mutation that either affects the gene directly or that affects the pathway that activates the gene. The consequence of the lack of DNA repair is that DNA damage accumulates. It is not repaired and inevitably leads to detrimental phenotypes such as cancer. So your DNA could end up like this, just in pieces. Octanogenes may be growth factors, protein kinases, GTP passes, or transcription factors. Growth factors are naturally occurring substances, usually a protein or steroid hormone, capable of stimulating cellular growth, proliferation, and differentiation. They are important for regulating a variety of cellular processes. Usually, they must bind to an extracellular or intracellular receptor to initiate a cellular reaction. Kinases are enzymes that catalyze the transfer of phosphate group from ATP to a protein in a cell. They function as a control switch in many cellular functions, turning a function on or off, and regulating other cellular processes. Many times they're involved in activating cascade reactors. Tyrosine kinases may be either membrane or bound receptors. A membrane is this, by the way. It's like, you know how an egg has a shell? Like the membrane is like the outer shell to a cell. Yeah. Also, I'm talking really fast and reading a lot of it at one time because I've been doing this all in one day. And it's been like 3 hours. And so if you see my lack of energy and I just stop talking for a second, it's because I'm really tired, but I want to finish this so I don't have to worry about it later. Okay, let's actually get back to our topic. I just noticed this picture isn't a cell. It's whatever it is. I don't know, and I don't care enough to go back and check. We're just gonna finish this right now. Okay. Many times they are involved in activating a cascade of reactions. Tyrosine kinases may be either membrane-bound receptors